The weather on Mars. What is the weather? Do you know? Well, we're going to find out all about it in a moment. What I'd like to do then is talk to you, and for the young ones, and I know they're not so young tonight, what I'd like to do is talk to you about the planet Mars. And it will all become clearer in a moment why I'm doing it. So, I don't know whether you know much about the terrestrial system, but Mars is the fourth planet from the Sun. And it is often referred to as the red planet, because the rock and the soil and even the sky have a red tone. Now, the planet was actually named by the Romans, and Mars was their god of war. But we can go through historical writings, and even the Egyptians had a name for the planet Mars. They referred to it as Her Deshur, which means the red one. Now, before space exploration, there was a broad consensus that there was extraterrestrial inhabiting the planet, and there was a good reason for that. Not these funny green-looking men on the screen, but genuinely, powerful telescopes looked out to this planet and they saw lines that crossed the planet. And there was a feeling for over 100 years that these were irrigation channels where Martians were planting seeds and growing their fruit and veg. And that was generally the view in most educated circles. You can't believe it, can you? That's the folly of science, young people. And until there was space exploration, then that was the broad feeling, that was the broad consensus. But things began to change when man started to explore this planet, and certainly through the Hubble telescope. Now, this was a picture that was taken of Mars in 2001, and the reason why that was a particularly important year, because this, in recent history, was the nearest that Earth was to Mars. It was merely 43 million miles. Now, the dots on the screen that you can see here, I hope you can see at the back, you can drop the lights if you want, but the various dots that you can see there speckled over the planet, it gives you an idea of the scale here. Each dot is 10 miles wide in reality. Now, the grey areas that you can see are valleys and mountains. So if a dot is 10 miles, you can get a sense of the scale of the topography of this planet. Thank you. Don't all go. So you get a sense of the topography here. The largest mountain on the planet is called, quite appropriately, Olympus Mount. And that mountain is 14 miles high. Now, I don't know if you've got any appreciation of the scale of that mountain. If I were to tell you that Everest was 2.5 miles high, then you get a sense of the proportions and the scale and the grandeur of this planet. Now, both Earth and Mars, and we're going to see in a moment that they have quite a lot in common, they are referred to as terrestrial planets. The reason being is that they are relatively small, they are dense, and they rotate at a high speed. And both planets are tilted on their axis. Now, I don't know whether you know about this. If a planet is tilted on its axis, in fact, in the solar system, only Mars and Earth have this tilting, round about 25 degrees. And the tilting on the axis causes weather and seasons. So that's one thing that we have in common with planet Mars, is that Mars also has seasons. It has a winter, it has a spring, it has a summer, and it has an autumn. Now, because this planet is further away from the sun, it is much, much colder. So the average temperature there on the planet, if you choose to go, take your woolies with you, it is around minus 80 for the year. During winter, it's minus 195 degrees Fahrenheit. On a warm day, round the equator, during the summer period, you can enjoy a 60-degree Fahrenheit but it will then be followed by minus 80 during the evening. So, yeah, you'll have to have a big suitcase to go there. It's a dense planet, and there is no human life, as we know, upon the planet. And that's really the reason, because of the composition of the atmosphere. You can see that Mars is mainly made up of carbon dioxide. These are heavy, heavy gases. And because 95% of the atmosphere is made by carbon dioxide, then what that will mean in reality is that the atmosphere of Mars is very thin. In fact, it's 1/100th the thickness of the atmosphere of Earth. So that's why you get such high variability in the temperatures. So just making a few connections so that you get a feel for what this planet is. Now that's the inclination of the equator to the orbit. So both these planets are tilted on the axis, and so they're slanted like that. And the reason that they're slanted, certainly for Earth, is that God has designed it in such a way that it would bring about weather, it would bring about the seasons, it would bring about the crops and the growth upon the Earth. And something similar is seen on Mars, though nothing grows there, of course. It does have this seasonal variation. Now, before we get there, I want to ask you a question. How long would it take you to get to Mars? I'm not talking about walking. I'm talking about jumping in a ship and flying to Mars. Anyone like to hazard a guess? Can you remember what I said? What is the distance between Earth and Mars? Yes, around about 40 million miles. But that's the shortest distance. In fact, because both Mars and Earth are on this orbit around the Sun, the distance between these two planets vary. It varies to a minimum of 40 million miles to a maximum of 140. So it depends upon what time of year you go. Anyone like to hazard a guess how long it would take you to go? What do you need to work out to find out the time that it's going to take you to get to Mars? Come on, those of you doing physics at school, I'm sure you're thinking through the formula. Distance equals... Is it speed divided by time or speed multiplied by time? Distance equals speed multiplied by time. So work it out then. What is the period of time? Well, let me just give you a few numbers. The fastest mission out into space was NASA's New Horizon that went to Pluto, and that went at 36,000 miles. So if I jumped on that spacecraft, roughly, how long would it take me to get to Mars? It's very easy here. I've got the answers. Huh? It's going to be years? Well, let me show you this. It's not years at all. You'll be surprised to hear. There has been many satellites and spacecrafts that have been sent to Mars, and this is the full list. And you can see, because of the distance between Earth and Mars, the times vary, and also depends on how powerful the rocket is. So the first one then took 228 days, and it was flown in 1964. Can you believe that? 1964, we were sending things to Mars. When I say we, it wasn't the White House household. It was NASA, okay? But in 1964. The shortest one was in 1969, 128 days. So 4 months. You could be to Mars. The longest was in 1975, 333 days. So, that's all very fascinating, Brother Stephen, Uncle Stephen. But why are we talking about Mars tonight? Well, the temperature outside, no, it has nothing to do with that. It is because 20 years ago or so, I did a PhD in mathematics for NASA. And it was all about developing a mathematical model for the Mars Pathfinder project. And it was a really fascinating thing to be involved in. And that's what I want to share with you tonight. And then we're going to bring it to the scriptures, because the wisdom of this world is foolishness in the sight of God. So don't misunderstand what I'm saying. But it is an interesting thing that I did, and I'd like to share a few things. So this was an illustration of what I was involved in, and we all got excited. And my job, I was handpicked, my job was to develop a mathematical model that when they landed the probe on Mars, they would understand the weather for up to 30 days, because they didn't know where they were going to land it, and they needed to ensure that it was robust enough to handle the various weather variations. So that's it, that's the background. Well, it was really interesting at that time, because it was a lot of fun. My landlord at university came into the truth, so there was a very positive thing that came out of university life. But also, I was meeting with some rather interesting individuals. Does anyone recognize this man? You probably don't, actually. If I said Sir Roger Penrose, does anyone know Sir Roger Penrose? Not know him personally. Anyone heard of him? The Emperor's New Mind. Has anyone read that book? Has anyone heard of Stephen Hawking? Yes. Well, he was the tutor of Stephen Hawking. So back home in England, there's two famous cosmologists at two rival universities. One is Sir Roger Penrose, and the other one is Stephen Hawking. And I was with Sir Roger Penrose. And so there he was for coffee each morning. It was interesting. It was just interesting to be in his company. There was another man at college with me, this man here. And yes, we do make jumpers like that in England. This man is called Andrew Wiles. And he was a mathematician at my university. I saw him each day. And then he solved something amazing. And he became then the most famous mathematician in the world. And it is Fermat's last theorem. Has anyone heard of Fermat's last theorem? Yes? I'm glad you've heard of it, because I'm going to ask you something in a moment. So Fermat died in 1665, and this was the equation he was trying to solve. You'll know that equation if I put n equals 2. X squared plus y squared equals z squared. What is that? Pythagoras. Yes. Lost in translation. Pythagoras, right? Pythagoras. Now, Fermat died in 1665, and he had a proof for Fermat's last theorem. But he said, I don't have enough space in my margin to give you the proof, but I've proved it. And for 400 years subsequent to that, no one could prove that this equation would not hold for x, y, z being whole numbers, 1, 2, 3, 4, 5, and n equal or greater than 3. So in other words, you can have x plus y equals z. You can find numbers that satisfy that equation. You can have x squared plus y squared equals z squared. But then you cannot find anything for x cubed plus y cubed equals z cubed, for example. Or a quadratic, and therefore, and thereafter. Now, it seems a very simple equation, and you would think, wouldn't you, if you didn't know this equation well, that you could come up with a number for 3, but you can't. And if you do, you'll be the best mathematician in the world. And so Andrew Wiles solved this equation when we were there, and it was really, really exciting. We had lots of media at the university, and suddenly he became very famous, and he didn't want to talk to us at coffee anymore. Now, for the young ones, and parents can get involved, I'm not going to try and ask you to solve this for n equals 3. My question for you, and there will be a prize, and I'll ask Uncle Bob to go out and get something really, really nice for you. There will be one prize. And I did this at Malatulian, and someone came away with a very, very nice prize, right? The numbers were staggeringly big that he came up with. So, here's the question, here's the problem. N equals 2. X squared plus y squared equals z squared. Anyone in the room, particularly the young people, I want you by the end of the week to come Uncle Stephen and show me the biggest number that you can find for that equation, and there will be a big, big prize. The prize will not be proportional to the number that you come up with, but there'll be a lovely prize for you. So let's get you going. 3, 4, 5 works, okay? 3 squared plus 4 squared equals 5 squared, okay? 9 plus 16 equals 24, 5. 7, 24, 25 works. You can work out the bigger numbers, okay? So, there's the problem for the young ones or older ones, young in spirit, young at heart. Come up with an answer by the end of the week, and Uncle Bob will give you something really nice. No, I will give you something really, really nice. So that's the challenge of the week. Now, what did I have to do? Well, I had to come up with these equations for Mars, and there hadn't been a probe sent to the planet for 20 years, and I had no data. There was no data at all. So I had to come up with some governing equations, and here was a set. Let me try and explain what these equations say. So, can you see that, by the way? Not that you want to, but can you? UVW are the directional speeds, okay? So it's velocity, right? The speed of stuff, namely the speed of wind. A is the radius of Mars. P is pressure. Omega. Has anyone done physics at high school? Would anyone know what omega represents? Yes, at the back? No? Or if I said Coriolis, have I pronounced that correctly over here? Coriolis force, it's the force that a fluid receives after a substance is rotated at speed, okay? That's the Coriolis force. When you've got a planet rotating quickly, you have a force on particles and fluids. And F is friction. So, in other words then, the change with respect to T, the change of speed, so the change of speed with respect to T is acceleration. Acceleration of any fluid on Mars is proportional to pressure, is proportional to the Coriolis force, and is proportional to friction. That's all I'm going to share with you tonight. Probably that's as much as I can remember, to be honest. But these are some of the equations that I looked at, and they look very simple. Well, that's what I had to solve. And it gives you an idea. So these computers, I was running these big computer algorithms, and it took 24 hours to compute each equation. Quite something. 24 hours. I have no idea. You probably could work it out on an iPad today. But then, back in the olden days, not quite at the slide rule stage, but back then it was 24 hours. And those are some of the equations that we had to solve. Well, what was fascinating was that these equations, and this is where it gets intriguing, because remember, and everything that we're looking at in the universe was created by God's almighty hand. Now, what we found on this planet, and bear in mind it's tilted on the axis, were things called baroclinic instabilities. You don't need to know what these are, but they are perturbations, they are perturbations, they are cycles of energy that are rotating around the planet in beautiful sinusoidal structures like sine waves. This is what we found. We're able to reproduce this in a model, and we found it through the data as well. Beautiful sinusoidal waves. And these were energy waves. And the important thing about it is that if you could model, if you could understand what we would say the underlying dynamics of these equations, if you could understand how these sinusoidal waves interacted with one another, then suddenly you can understand the governing equations of the planet, and you can start predicting fairly accurately, it turns out, the weather. Now, it's much easier, or it was then, it's much easier to predict the weather on Mars. Not that you'd enjoy it in another way, but it's much easier to predict the weather on Mars because there's no water, and water on this planet creates an extra variability, and often makes some of these equations almost impossible to solve. So it was relatively easy. I say relatively, it was pretty tough, but relatively easier to solve these things. And this is some of the structures that we found. Look at those lovely structures on Mars, right? These baroclinic, right? Going around the planet in these beautiful formations. And in my model, this is what we were able to find. And we found, it's called a wave 2 and a wave 3. So at the top, you can see these circles here, these concentric circles, one's in orange and one's in blue. And I just want you to imagine it's a wave. So the orange is the crest, and the blue is a trough. And the perimeter of Mars is 36,000 miles. And what we were finding in this model, and what we were able to reproduce with the data, is that these waves, a wave 3 would mean that there were 3 crests on a wave that went all the way around the planet. Isn't that amazing? And behind it, as a secondary wave, was another wave with two crests. And there were other waves, but these fundamentally were the primary and secondary wave. They're waves of energy that went round the planet. And the way that they interact determined dust storms, determined the weather, determined everything that was taking place upon the earth and on the planet at that particular day. It was amazing. We would call those in mathematics low-dimensional models, where you try and distill all the energy, all the variability of a planet, and you try and distill it into a handful of equations. And that's what we were looking at. But think about the God that created this planet. These two types of waves. That's all it is. That's the underlying dynamics. And the way they interacted determined everything on the planet. Isn't that amazing? You've heard of order and chaos. There's nothing chaotic in God's creation. We might look outside and see the weather and think, wow, especially in Britain, what a chaotic day. There's nothing chaotic about it at all. There are these beautiful, elegant, mathematical equations governed by Almighty God. It's the way that they come together brings about the variations of the day. Quite amazing. Well, how do you get to Mars, if you're thinking about it? How do you get to Mars? Well, they both orbit the sun, and you can't just set your sat-nav and travel to Mars. You have to go on an orbit. So first of all, then, you have to begin on the Earth's orbit, and you travel around the sun, and then you need a rocket to get off your orbit and to then connect to the Martian orbit. You can't go directly. It's not like traveling to Washington from here, and you set your sat-nav and you drive along a long straight road. It's not like that at all. You have to go on the orbit, and then you have to come off at a tangent of one of the orbits and go to Mars. And this is what happened. So we developed the model, and off it went. And it started, the launch was December the 2nd, 1996. Yes, I am as old as I look. And it left, it went onto the trajectory of the Martian orbit, and it landed on Mars on the 4th of July, because that's the way it was planned. 20 years tomorrow. I wish I'd given this talk tomorrow. 20 years tomorrow, this planet received this probe, the Mars Pathfinder. It was a relatively expensive project. It was $200 million back then, paid by, in the main, the Americans. And that's the Jet Propulsion Lab assembling the probe. Now, those of you who can remember a little bit about this orbit, that's the one that introduced the parachute. Do you remember that? It was in all the papers back home in England. The parachute. As the probe broke into the atmosphere of Mars, then it released a parachute and it landed. And there were these cushions here, these airbags that was going to cushion the impact. And it landed very safely. And this is where it landed. It was felt that this was the most rocky part of the Martian topography, and that it would be best suited here. And the plan, the intention was for the Mars Pathfinder, the little buggy, to go around and to collect dust and rock samples for 30 days. That was the plan, and a few measurements of the atmosphere. So it landed in Ares Vallis, the Valley of Ares. And that's the picture of the rover as it was released from the ship there. Now, so we're getting to exciting times now. This is when the door was first released. I know it's not the clearest of pictures. I hope you can see that. But can you see the rover in the background? Can you see that? The rover's there collecting the samples just outside the craft. Now, you won't be able to see that, but what you might be able to see here in the distance, this is referred to as the big crater. So there's in Valley Ares, and the Pathfinder looks out, and it can see here the big crater, and then here the Twin Peaks. We're going to look at those in a little bit of time, but the big crater and the Twin Peaks. And I need to look quite closely here, but the NASA scientists named these rocks, and all these rocks that you can see named were picked up and brought back. And some of them had very funny names, right? So here's a few NASA scientists, and they're quite creative with some of the names here. Let me just read out. Pooh Bear is one of them. Scooby-Doo is another. Shark is another. Barnacle Bill. So they obviously had too much time on their hands. But these were all the rock samples that were collected on the planet. Now this is the landing here. We've got the Twin Peaks. It's 1 kilometre. I know you can just see that. And then we've got this big crater here, which goes all the way down here, which is about 2 kilometres away. And it's never going to reach that. In fact, it only went about 100 metres. That's all it did. But it could see all these things on its little telescope as it beamed the pictures back to Earth. No, that's not Australia. I was going to wind Neville up with that, but he's not here. So no, that's not Australia. That's Mars. And these are some of the rocks that this little rover has got to navigate around. And so it went 100 metres ahead, and these are the various rocks that it got up close and personal with, right? All of them were named, 100 metres, that's all it did. Now, all very interesting, isn't it? All fascinating, brothers and sisters and young people. Beamed about a lot of data, 2.6 gigabytes of data, 16,000 pictures of the...
Green, it's a lot brighter.
Oh yes, that's much better, thank you. Yes. There's nothing of interest, but if I need it, I'll use it. But thank you all the same. Anyway, so he has to navigate around these various stones and part of the topography. It was all very, very difficult. But you know, man thinks he's so good, doesn't he? All this data was being back. It lasted more than a month. It actually lasted 3 months. And my model turned out to be quite good. All very nice. All that effort. And all the rover could do was go 100 meters. That's all it could do. And it picked up a handful of stones. And how much information really could we gather from Mars? It's like landing a probe in the canteen here at Shippensburg University and predicting the weather in Birmingham. Isn't it really? A little part of the planet. So you young people, yes, of course, this sounds so grand and so clever, but how clever is it really to God? It's nothing, is it? It's absolutely nothing. But what struck me, and this is one of the things I loved about mathematics, when I went to university, my father encouraged me to do something that didn't challenge my knowledge and my beliefs in Scripture. And I can tell you, and I spent a long time at university, it enhanced my appreciation of God. It really enhanced it. Man's menial effort of 100 meters and picking up a couple of rocks, and I saw the beauty of that planet and how it can be described by these baroclinic and barotropic instabilities and how they interact with one another, and they can be expressed in 4 or 5 elegant equations which are infinitely dimensional. That's what you call it in mathematics. Oh, and amazing. So with that, can we open up our Bibles, please? And as we go there, just keep it on a little, or off, just for a moment, please. Of all the pictures that were beamed back, these were the most beautiful. Not the rocks, not the data, but the sunrise and the sunset on the Martian horizon. God is in control. Even a planet in our solar system that has nothing to do with Earth, there is divine order. That is the God whom we serve. Isn't it wonderful? And so let's just open up our Bibles and go to a few passages, really for the purposes of our young people tonight. Isaiah chapter 40, and this is what God says through the prophet here. Verse 22. It is he that sitteth upon the circle of the earth, the inhabitants thereof as grasshoppers, that stretcheth out the heavens as a curtain, and spreadeth them out as a tent to dwell in. God looks at his creation, however good it was. They are grasshoppers in his sight. They are pygmies compared to the majesty of Almighty God. That's something we mustn't forget. In all the science of today, next door in my department, you know who used to work there? Richard Dawkins. The wisdom of this world is foolishness in the sight of God. We are grasshoppers. And in the 10 years that I studied and taught at university, science changed on its head. There's always a new thing. But with God, there is no shadow of turning. Don't get caught up, young people, with the science of today. Yes, study it if you need be. But don't get caught up. Science does not have the answers. The chapter which we had read, the psalm, this wonderful psalm, Psalm 8. This Psalm of David here. Some would suggest that this was a psalm actually penned by David as he took Goliath down, as he removed his head and as he reflected on the majesty and the grandeur of Goliath. He wrote this psalm. Let's just read a few words together. O Lord, our Lord, verse 1, how excellent is thy name in all the earth, who has set thy glory above the heavens. It's a rhetorical question, isn't it? Verse 3, when I consider thy heavens, the work of thy fingers, the moon and the stars, which thou hast ordained. What is man that thou art mindful of him? And the Son of Man that thou visitest him? Read those words, brothers and sisters and young people. Read them. David here is urging you to read these words and ask yourselves the question, what is man that God takes an interest in us? What is man? Yet in spite of all that, God does take an interest, such an interest that he gave his only begotten Son. And I want to finish in one of my favourite sections of God's Word. Can we go there? Genesis chapter 15. Genesis chapter 15 here, this wonderful, wonderful chapter here. After Abraham has met Melchizedek, and suddenly Abraham, for a brief moment, he loses some of his faith. He doesn't know when a child is going to come. He fears that he's going to be childless, and God now gives him these reassuring words. And it is here, for the first time, that Abraham believed in the Lord. And it means there in verse 6 that he believed as a child. Hebrews 11 tells us that he followed God as God led him to a land that he didn't know about. But that was a rational faith. God spoke to him and he responded. It's not a rational faith anymore here in verse 6. He believed as a child. And what did he believe in? Well, look at this. Verse 5, young people. God brought this man of faith forth and said, look now, Abraham, toward heaven and tell the stars, if thou be able to number them. And he said unto him, so shall thy seed be. It would be an innumerable host, brothers and sisters. And for the young people tonight, you do have clear nights here, unlike back home. So why don't we all look at the skies tonight and think of the promise given to Abraham? Because the promise to Abraham was that as you look up and you look at the stars in the sky, twinkling in the darkness of the firmament, They are God's seed. But it's more than that. As Abraham looked up, he's being told that one of them represented him. And what an encouraging and comforting message that is, brothers and sisters and young people, when you look up into the infinite of space. One of those stars represents you. You. But you've got to believe it in faith. Thank you.